All right. So a rate diagram, we have removed some H2O. So here's our H2O. It is a product, which means that we will have fewer collisions between product molecules. Which means that the reverse rate is slowed. And the forward rate, nothing has happened to it because we've done nothing over here. No change. So in our rate diagram, the first thing we need to do is put rate on the y-axis and time on the x-axis. And we have our starting okay, so there's our forward, there's our reverse. I'm a little concerned. I'm seeing people do this. They need to be like, they should literally, like if I were really drawing it appropriately, I should actually have it like this, right on top. Why don't I put it right on top? Because you can't see it if you put it right on top, yes? So instead, what we do is we put our forward like this, and our reverse is like just barely underneath so you can actually see the two clearly, okay? And in this case, our stress was the decrease in H2O, and so our stress causes the reverse rate to be slowed. So that our stress results in the reverse rate slowing down. So the reverse rate goes down, no change to the forward rate. And then the two are going to, okay, steep, shallow, flat, steep, shallow, flat. And this is where I would want to use a ruler because I'm doing a terrible job at drawing it close to the other one, but whatever. It's fairly close, okay? Did that help? Was that what you were asking about?
Yeah.
Yeah?
Like,
and then for the concentration diagram as well?
Yeah, because like I duplicate the sense of like NO decreases by 2x.
Uh-huh.
H2 decreases by x, but why will like N2O increase by x?
Yeah, okay, so let's take a look at that. We have H2O goes down, right? Because that was our stress. And then it goes up. Does it ever get up to its original value or go past it? No, it always stops somewhere short of that level there, okay?
But why does N2
Why does, there is no N2.
I mean N2O.
N2O does not increase. Did I draw it increasing in the answer key? Oh yeah, it does. Oh no.
You drew it.
Yeah, it does. It does increase. Why does it increase? Because we are making H2O, yes? Well, we decreased it, but then the system makes H2O.
Oh, yeah.
Okay, we decrease H2O. And then the system makes H2O. Is it possible for the system to make H2O without also making N2O? You can't make one product without the other. If you're making one product, you are also making the other product. So therefore, the system must also make the other product along with the H2O. Okay, and so that's also going to go up, and because they are one-to-one, that's going to be X. So we have X. I did notice a couple people yesterday, I can't remember if it was this block or the other block, they drew their X here. That value is not X. Okay, the value that is X is how much the system makes or uses up. So X is always the change in concentration due to the shift. Okay. And because we are making products, what must we be doing to the reactants? We must be using them up. And so H2 is being used up. I'm going to make it red just because it's going to overlap by the size I've drawn them, and it's going to be a little bit ugly.
It should be like somewhat
Hmm?
It should be like the proportion should be somewhat close.
The proportion should be, I mean, if you could draw it perfectly so the proportions were exact, then yes, that would be fantastic. Are we all that great of artists? Probably not. If you have like a grid, like if you have graph paper, right, then you can probably like draw the lines where they're supposed to be. Does that make sense? But yeah, just do the best you can. And then finally, NO has a coefficient of 2. So it is going to go up by not just 1x, but 2x.
But NO should go down.
Oh, it should go down. Duh. Sorry. You're absolutely correct. Because we're using up reactants, it should go down by 2x, which again is going to make for a fairly ugly diagram because I drew my lines a little bit too long. But that's okay. I'm going to make it work. 2x. There we go.
So also for the answer key for LeChatelier.
Uh-huh.
It says therefore the shift moves to produce N2O, and to bring N2O back up should be H2O back up.
Oh yeah, it should be H2O. Okay, so this one, where is that? Is that on the previous page? Yeah, okay. Fix answer key to refer to H2O. So if you guys didn't catch that, the answer key refers to N2O, but it should say H2O, okay? Anything else from any homework? I have to say I bragged about you guys yesterday to my period 8 class because I gave them time to work on stuff and they did not use their time well at all. There were only about like 4 or 5 people in there who used their time well. You guys used your time when you were working yesterday really well. You asked really good questions. You got lots of good clarification. That's going to work well for getting you like good understanding and good ability to write things in a clear way. Okay, so good job. All right. So today we are going to move on to the stress of changing volume and pressure, which is on page 38. Pressure and volume are inversely proportional. Do we know what inversely proportional means? It means if volume is decreased, the pressure will increase and vice versa. And that is because pressure is essentially how often and with how much force are the particles bashing into the walls. I'm going to put sort of. It's sort of equal to how often and with how much force particles are bashing into the walls. Okay, so if we're dealing with gases, we have to have a system that involves gases. So if we're doing pressure and volume, it has to involve gases. So we've got a gas and a gas and a gas, and we have a 1:3:2 ratio between those three. Okay, if we decrease the volume, what happens to the pressure? Increases. If the pressure increases, what happens to the rate of the forward reaction? It speeds up. So the forward rate speeds up. Why? Are the speed of the particles faster? Beta? Yeah, the particles are all closer together, so there's going to be more collisions. What happens to the rate of the reverse reaction? What we did, remember, is we decreased the volume.
So the reverse rate should also increase because both ways are the same.
It should also increase because the particles are, if I've squished the container, I've decreased the volume, the particles are closer together, so there will be more collisions.
Oh, because like the product decompose, right?
At the same time.
At the same time and at the same place.
Yeah, in the same time and in the same place. What you always have to realize with a volume change is that you are changing the container, and the container is for both the reactants and the products. They're all in that same container together. You can't just change the volume of the reactants. That doesn't work because everything's in the same container. So the volume is smaller. Therefore, the particles are closer together. Therefore, more collisions. Oh, I saw a funny meme yesterday. I thought it was cute. Okay. Which rate of reaction is sped up more? The forward or the reverse rate, and why? Well, it turns out the side with more gas molecules, not just any molecules, you have to say gas molecules, experiences a greater change in rate. Okay, so on our left-hand side, we have one molecule of N2. We have 3 molecules of H2. That gives us a total of 4 molecules. 4 gas molecules. Whoops. And over on the right-hand side, we have 2 NH3s. So we have on our right-hand side 2 gas molecules. Therefore, if the side with more gas molecules experiences a greater change, which rate will experience a greater increase? So if more gas molecules experiences greater change in rate, is it the forward reaction or the reverse reaction which experiences the greater change in rate? The forward. Because there are more gas particles in the reactants for the forwards reaction. More gas particles in the reactants. Therefore, the forward reaction experiences. By the way, if you want to abbreviate experiences, forward reaction experiences a greater change in rate. Okay, I feel like I've written that 3 times now, so I don't know that you need to really write that the 3rd time, but that's okay. Now, you don't actually need to understand why, okay? So my question to you is, do you want to go through the explanation as to why the side with more gas molecules actually experiences a greater rate of change, or do you not want to go through the logic of it? It's up to you.
Would it help us?
It depends on whether you like understanding things. Or you can just be like, more gas molecules, bigger change in rate. Sure, we'll do it? Okay. You can just ignore me if you're just like, I just want to memorize that and be done. Okay. So why does the direction with most gas molecules as reactants experience the greater change? Let's think about what happens to the concentrations if we cut the volume in half, if we have the volume. Okay, so what happens to our concentrations when we cut the volume in half? So we are going to go from 1 liter with 4 reactant molecules, 4 molecules per liter, to 0.5 liters. Okay, so we've cut the volume in half. Our original concentration was 4 molecules in 1 liter, 4 molecules per liter. Our new concentration is 4 molecules in a half a liter. So what is our new concentration? 8 molecules per liter.
Because we have to like make the numerator the same.
Yeah. And when we do per liter, we're never like per 7 liters or per half a liter or per, it's always per 1 liter. So if we have the concentration, or sorry, if we have the volume, what happens to the concentration? It increases by how much? By what factor? By a factor of 2. So the concentration doubles times 2. So what was the actual change in concentration? What did I write here? Trying to remember.
Oh, the threshold decrease. So
I'm just trying to remember what it did. Oh, so the change was 4 molecules per liter. Okay, so we went from 4 to 8. So the change was 4 molecules per liter. In our products, because we only had 2 gas molecules, okay, so here are our 2 particles in 1 liter. That's 2 molecules per liter. Okay. And when we cut the volume in half, when we half the volume, what happens to our concentration? Our concentration increases by how much? Doubles. And you can see that because we no longer have 2 molecules in 1 liter. We now have 2 molecules in 0.5 liters. And if we have 2 molecules in 0.5 liters, how many molecules per liter is that? 4 molecules per liter. So going from 2 to 4, our change was 2 molecules per liter. Which of these two was the greater change? The reactants. So we had a greater change in concentration. Therefore, the forward rate is affected more. In the products, we had a smaller change in concentration. Therefore, the reverse rate was affected less. So therefore, our forward rate increased more than the reverse rate. They both increased, but the forward more than the reverse. Both rates have increased, but since the forward rate increased more, the forward rate is greater than the reverse rate, meaning we are no longer at equilibrium. Yeah, because they're no longer equal. And if the forward rate is greater than the reverse rate, what are we making faster, products or reactants? Products, right? Because remember, our forward rate is faster than our reverse rate, and so we are making products faster than we are using them up. So the system is shifting right. And let's just make sure we make a note here. You do not need to be able to explain this. Okay, and that when I say this part, I mean this here. You should be able to say both rates have increased. The forward rate increased more because it had more gas molecules. Oakley dokley. There is a more mathematical way of doing it. I'm not going to go through this because do you guys feel like you need any other way? No, I think we're good. All right. So the greater the amount of gas molecules, let's put a box around gas and let's highlight it or put a star beside it or something. Because I will say one of the most common things that students do is they forget to say gas molecules. They just say molecules, and it has to be gas molecules because pressure and volume do not affect aqueous, they do not affect solids, they do not affect liquids, okay? The greater the amount of gas molecules on a side, reactants or products, causes a greater change in concentration, which means it causes a greater change in rate. And in this case, therefore, the forward rate increased more. So if we were to show our original equilibrium, we might show our arrows like this. You'll notice I've made them not too big because I'm going to have to increase them. When we decrease the volume, both of them get bigger, but the forward gets more bigger. My gosh, why do I have this so many times? So the forward rate is greater than the reverse rate. So we're making products faster than using them. Therefore, we are shifting right. Okay. How are we doing with that concept? Good. All right. Excellent. Let's graph what happens when we decrease the volume. So we have a rate diagram. And we have time. And we're going to have our forward rate and our reverse rate. And remember, they should start as close to one another as you can physically draw them. When we decrease the volume, what happens to the forward rate? The forward rate increases. The reverse rate also increases. Which one increases more? The forward rate increases more. So it doesn't matter by how much more, but you would say, okay, my forward rate increased more. I need to draw that as a straight line, not as a wiggly woggly line. Let's try that. There's my forward rate. My reverse rate increased, but not by as much. Okay, and sometimes I like to just for myself make a little line there so I can see where my reverse rate made it to, but you don't have to do that. That's our stress. And then our shift, steep, shallow, flat. Steep, shallow, flat. So this was the stress, made the reverse rate go up. And then the shift makes the reverse rate go up even more until it matches up with the forward rate. For our forward rate, this was our stress. And this here is our shift. Is good? Okay. Are we ready to move on to the concentration diagram? Okay, so here's our concentration. Here's our time. Because I'm lazy, I'm just going to do N2, H2, and NH3. The size of the change due to the stress is going to be wrong. I'm going to show you what would happen if I have the volume. Do not draw this, okay, because it's going to make a mess. Okay, so if I were to halve the volume, all of our concentrations would, what would they do? All the concentrations would double. Don't write this down, because it's just going to make a mess. All right, so let's double our concentration of NH3. So I have to make it twice as high as it is right now, which would take the NH3 up to here. Okay? You see how it's getting messy already? And then I would have to double my H2, which would take my H2 up to, it'd have to be twice this much. So it would have to go up to here, right? Yeah, because I'm doubling it, yes. And then my N2, I would have to get all the way up, I would have to have twice that much. So that would mean that I would have to go all the way up to here. Do we like this? Is this easy to read? No. Therefore, the size of the change due to the stress is going to be wrong. We are deliberately going to just make them smallish changes each so that the graph doesn't look stupid. Okay? So what we're going to do is we're going to say, we're not going to worry about the proportionalities. Okay? We're just going to say that all the concentrations go up. We decreased volume, therefore all the concentrations increase. Don't worry about how much. So I go up, up, up. If you want to make them all the same, that's fine. You can make one bigger than the other. I just find it's like tidy. Yes? So are those the wrong amount of changes? Yes, they are, but does that look like easier to read? Yes. So just make them, all the concentrations go up. Don't worry about how much, just make the graph look nice. So that is for our stress. So the stress, don't worry about it. Now, remember we are making product faster than we are using it up, so we are shifting to the right. As we shift right, what do we make? We make products. And what do we use? We use reactants. That means our concentration of all our products will go up. So this is in our shift now. All product concentrations increase, all reactant concentrations decrease. So product is NH3. I'm going to draw my shifts in red because then you can see the difference between the shift and the stress, or you can just put a little dash there saying that's the end of my stress and now I'm going to start my shift, and my shift is going to go up by, let's just say, that much. Okay, steep, shallow, flat. I should not have written that. That's going to get in the way. Too much stuff. If you need whiteout, you can have some whiteout. Okay, what's H2 going to do? Is H2 going to increase or decrease? It's going to decrease. By how much? By 3. And remember, NH3 went up by how much? 2. So this is going to go up by 2x. And sometimes I like to just draw 2 arrows. You don't have to. I just like to say that's about how much 1x is 1 arrow. H2 is going to go down by 3x. So I'm going to say I need to go down by 1, 2, 3. So it's going to end up about here. Okay. And then N2 has a coefficient of 1. So it's going to go down by x. Is good? Okay. Changes in volume and pressure get kind of, like the diagrams get kind of messy. So you can imagine how much messier they would get if we actually did it proportionally. You still have to be, shifts have to be proportional to the coefficients. But the key thing to remember is that when you change the volume, not just one of the concentrations change, but all. the concentrations change, and they all change in the same direction. But don't worry about the size of that change. Just be like, ah, it changed. And this just says, in an ideal world, we would make the concentration changes due to the stress proportional to the coefficients. But no, that wouldn't be proportional to the original concentrations. Fix. Do you guys know this symbol?
No,
Is proportional to. Is proportional to. Anyway, we've already talked about that, so the fact that it's not very useful doesn't make that big of a difference. The changes due to the shift, though, should be proportional to the coefficients. All right. And I'm going to make that look more like the proportional symbol. Okay. LeChatelier's principle. We're going to try out a little simulator here. Okay, I've got like a little picture, but we're going to try the simulator because it's kind of fun. Let's see if it works. Fingers crossed. Sometimes these sites go down since I've published, but hope for the best. Looks promising. Okay. Oh, here we go. Okay. So we have, this is our N2. Do you remember that brown gas we had? Yeah. So we had NO2, which is the brown gas, and N2O4, which is the colorless gas. Yes. And you can see here, we have some NO2, which look a little bit like water. And then we have N2O4, which are the bigger molecules. Yes? Now let's remind ourselves, in the equation, there are two NO2s on the left, and there is only one N2O4 on the right. So, if we squish this container, let's start as big as possible. When the space is as big as possible, we have almost all NO2. Yes? Almost all NO2. So there's a certain pressure. What happens to the pressure when we squish it? Pressure goes up. The stress is the increase in pressure. Ah, says the system, you increase the pressure. What does the system then want to do? Ah, the pressure's getting too big. I will make the pressure. Ah, pressure's too big. I will make the pressure small. Okay? So we make the pressure big. The system says, I will make the pressure small. How does it do that? It shifts to the side with fewer molecules, because fewer molecules will decrease the pressure. Yes? Now, we're in a new equilibrium here. You can see we now have only two of the little NO2s, and we have a lot of the N2O4s. Now we're going to stress this system by increasing the volume. Increasing the volume decreases the pressure. The system says, you have decreased the pressure. The system says, I will do what? No, we're in charge of the volume. Ms. Spence is in charge of the volume. Ms. Spence decreases the pressure. What does the system want to do in response? It wants to increase the pressure. So if we decrease the pressure, the system wants to increase the pressure. Remember, what does LeChatelier's principle say? When a system at equilibrium is stressed,
it will try to get back to
not just that it will try to get back into equilibrium, the system will shift. What was that? The system will shift in order to minimize the stress. So if the stress is too little pressure, the system is going to shift to make more particles to bring the pressure back up. Which side has more particles? That would be NO2. And you see, the bigger the volume, we end up with more NO2. The smaller the volume, we end up with more N2O4 because the system is trying to keep the pressure constant. Okay? So, if we decrease the pressure, decrease the volume, increase the pressure, that is our stress. Okay, so you can see here is our initial volume. The system is stressed. The system shifts. And so we take two A's, which are the red ones, and we turn them into one B particle. Yes? Pressure is too high. How many particles are in this box right here? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Gas molecules. The system says that's too much. My pressure is too high. I liked it back when the pressure was this big. This has 17 gas molecules. Down here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 gas molecules. The system shift to the side with fewer gas molecules to bring the pressure back down. Is good? Okay. So this is a little script you can use if you want to. I'll wait for you to finish writing before we carry on. So in this case, our stress was an increase in pressure. When we increase the pressure, will the system shift to the side with more or fewer gas molecules? Fewer gas molecules. And in this case, that would be to the right, because we've only got one B on the right. So it'll shift to the right. The smaller total number of total moles of gas will bring the pressure back down. You don't have to explain this. This is just fewer gas molecules means fewer collisions with the sides of the container, and therefore the pressure decreases. So we stressed by increasing the pressure. The system then tries to decrease the pressure. Let's look at what happens when we increase the volume. We increase the volume. which means we decrease the pressure. The system says, ack! Pressure too small. Must make more gas particles to bring pressure back up. So the stress was a decrease in pressure. So will this system shift to the side with more gas molecules or fewer gas molecules? More gas molecules. And in this case, more gas molecules, is that our left or our right side of the equation? There's our equation in yellow. It's going to go to the left. And then our greater total moles of gas will bring the pressure back up. You don't ever need to write this part. Okay, so now we have more gas molecules, means more collisions with the sides of the container, which means the pressure increases. Yay, less stressed. Is good? Okay. So you remember those little scripts from last day that we had with the concentration? These are scripts that you can use for for changes in pressure and volume. What am I trying to say? There we go. Okay. So this is a rate explanation. So this is rate when we increase pressure, when we decrease volume. This is the rate explanation when we increase volume, decrease pressure, or sorry, increase pressure. Oh my God, what is wrong with me? There we go. I don't know that reading over this is going to be useful. Do you feel like me reading it to you will be useful? Yes? Okay, let's read through it. All right. So if I increase the pressure, since the overall space is, oh yeah, we can go through this. Since the overall space is, we decreased our volume, since the overall space is decreasing, or you can just put decreasing, all the particles collide less frequently. So our reactant particles, our product particles collide less frequently. Therefore, both the forward and reverse rates decrease more frequently. Therefore, both rates increase. Thank you guys for catching me. More frequently, therefore, both forward and reverse rates increase.
Wait. This is so we can literally copy this down.
Yep.
Because there's two versions of it.
There's two versions of it, yes.
So that means for the other one, we have to like somewhat figure out what's happening.
Well, we'll go through the other one as well.
Not,
yeah.
Like, not the other one.
The LeChatelier. I think it's on the next page.
No, not the other.
LeChatelier.
Not for pressure, for the other one. For the yesterday's lesson.
For yesterday's? Oh yeah. Well, we had scripts for that too.
We don't copy it one of.
You can if you want to. It's up to you, right? So it's up to you whether you like having a script or whether you would rather, internalize it and just be able to go speak off the cuff, so to speak. Yes? The direction with more gas molecules as reactants will have a greater increase in rate since the concentration of gas molecules is affected more. Therefore, the direction with more gas molecules will be faster. Now, this, honestly, I wouldn't do this one word for word because this doesn't let you know. It's like, you could be more specific. You could be like, oh, my reverse rate has more gas molecules, therefore it will experience a greater increase. And you could just leave it at that. So for example here,
Honestly, there's enough practice in the book for writing.
no, you may need to use your own paper. Yeah?
So I feel like there might not be enough practice in the book because like practice in the book for writing each explanation because you want to get any grade for it.
Then you practice writing it.
Or just memorize that.
Yeah. Yeah? If you want more, I can just print more. Okay? Therefore, the system is shifting and then you'll just say whichever direction it's shifting. All right, if we decrease the pressure by increasing volume, the overall space is bigger. Therefore, all particles collide less frequently. Therefore, both the forward and reverse rates decrease. The direction with more gas molecules as reactants will have a greater decrease since the concentration of gas molecules is affected more. Therefore, the direction with more reactant gas molecules will be slower. So whichever direction has more gas molecules, it either ends up faster if you've increased the rate, or it ends up slower if you've decreased the rate, because the change is greater. Therefore, the system is shifting, and let's just say which direction it shifts. But what happens if there are the same number of gas molecules on each side? We haven't talked about that yet. That's a new and different thing. If there are the same number of gas molecules on each side, both rates will increase or decrease the same amount. And if they both increased or decreased the same amount, are we at equilibrium still?
Yeah.
Yes. So our original rates would be like this. Our new rates would be like either that or that. So there will be no shift. You will see a change in all the concentrations due to the stress. But you will see no shift. And now I'm going to give you some good news. The likelihood of me asking you on a quiz to explain the shift in terms of rates for a pressure change is slim to none, because it is big and it is bad. Do you know what I mean? Like, there's a lot of moving pieces. Okay, definitely explanation in terms of rates for concentration. We will do temperature next day, and definitely you can explain temperature in terms of rates. But for pressure, although we've gone through it, and I think it is really worthwhile in terms of your mental ability to understand it and to piece it all together. Feel free to explain in terms of rates if you want to, but I probably won't ask it to you on a quiz. Okay? Probably what I will ask you is I will ask you for LeChatelier's explanation. And this one's fairly straightforward. The stress was an increase in pressure by decreasing in volume. If it was an increase in pressure by decreasing in volume, the system will shift to the side with more. Oh, hang on. Draw yourself a picture. You'd be like, okay, I decreased my volume. Do I want to go to the side with more gas molecules or fewer gas molecules in this new volume? Fewer. Don't be shy about drawing a picture because it helps make it visual. To bring the pressure back, down. If the stress was a decrease in pressure by increasing the volume, so we started little and we ended big, the system is going to shift to the side with more. You can just think, oh, I got all that extra space. I need to fill it up with more molecules. Yes? Or up here, you'd be like, oh, I've got so little space. I need to go to the side with fewer gas molecules because there's not as much space for everybody. Okay? And that's going to bring the pressure back up. If there are the same number of gas molecules on each side, shifting will not be able to counteract the change in pressure. So there will be no shift. What did I write here? You will see a spike. But no shift curve. It'll just go flat. So before we finish up today, let's make sure we get a graph going, okay, so that you know how to do this before you go home. Rate diagram. We have this system 2, we have H2 plus I2 in equilibrium with 2HI. rate, time. This is a situation where you've got two gas molecules on the left and two gas molecules on the right.
So we don't change.
Forward. Oops. Reverse. They start out as close together as you can possibly make them. And then here, at this time, we increase the volume. What happens when we increase the volume? The pressure decreases. What happens to both our rates when the pressure decreases?
Decrease the volume, pressure goes up, so the reaction rate goes higher.
So we went from a smaller volume to a bigger volume. More collisions or fewer collisions? Fewer collisions in bigger volume. So both rates will decrease. Same number of gas molecules on each side, but so they both decrease by the same amount. And because they're already equal, they just stay equal at the new . Okay, same number of gas molecules on both sides, so both rates slow by the same amount. There we go. Okay, concentration diagram. Concentration, time. At this time here, we increase the volume by decreasing the pressure. Remember, if you're having trouble visualizing what's going to happen to the concentrations, draw your original volume, small, and draw your final volume, big, and say, what happened to my concentrations if all of a sudden the volume got bigger? All the concentrations decrease. Do we care by how much they decrease for pressure changes? No, we just want it to look nice. Nice, nice, nice. There's no shift. What's that going to look like? No shift, no shift, no shift. Well, if we're not shifting, why would the concentration change? Right? All right. And for homework, you guys can finish 2.2c.
Right.
If you understand it, it doesn't need memorizing. But if you have trouble understanding it, yes, you can memorize it.
No, it's like more like, oh, I might forget to write this, forget to write that.
Yeah. So it is worth it. Yeah. Yeah, I understand. Thank you guys very much. I'm halfway through marking your block. I have not yet touched the other block. So I will be done by Monday. Should be anyway.